Hello children, welcome to channel Sube. Children, today I am going to discuss question number 3 from the MCQ part of 2021 Physics new syllabus paper. Bending of light when passing a sharp edge is due to the answer. First one reflection, second one refraction, third one interference, fourth one diffraction, fifth one total internal reflection. So let us try to do this, solve this problem. To solve this, we don't have to do any calculations, or we don't have to do any arguments. Just we have to revise the lesson. If you remember the lesson, you can just select this answer. Because in the lesson we learn what is reflection and what is refraction and what is interference, then diffraction, then what is total internal reflection. So children, let us start from this fourth one, diffraction. Let us discuss what is diffraction is. What diffraction is. So this edge, sharp edge, we need a sharp edge to show diffraction. So normally we use the ripple tank to show this in the school. So it is a normal tank, so we fill water and place a glass cube of glass, so that some length is out of the water's surface. So like that, when we after arranging it, we can start the vibrator, then waves begin to come like this, propagate like this, and here they fall on this glass cube, or what they say in this question, sharp edge. So you know these maximum amplitude points are called crests, or these are crests. So we can draw a line to join these crests like this, and next one like this, next one like this. So like this we draw lines. So these lines are called wave fronts. So we use, instead of waves, we use wave fronts to describe this phenomenon. So now I am going to draw wave fronts instead of those waves. So this one is a wave front. So like this we draw wave fronts. So the distance between these wave fronts must be equal, that is equal to wavelength lambda, like this. That is enough. So what is diffraction is this wave front after passing this edge, what happens? This plane wave front, so we call these are plane wave fronts because they are straight. So the wave front bends like this at this edge, like this bends. Therefore the direction of propagation changes. So the next wave front will be here like this. So next one will be like this. What happened? Like this, little bit shift little by little towards the edge, like this. So to find out the direction of propagation, so earlier initially they came like this, to this direction, to right, left, from left to right came, and at this midpoint they passed this edge without bending here because it is far away. Then here what happens, closer to this edge, the direction is this way, because the rule is to find out the direction we have to draw a normal, that means perpendicular line to this what we call this wave front. So spreading like this, you can see waves spread like this from after passing this edge. So this phenomenon is called diffraction. So this length is lambda, wavelength lambda. So after diffraction, this wavelength is also lambda, it doesn't change. So velocity also same, before diffraction and after diffraction, velocity also same, and frequency also same, because the same source used, therefore frequency doesn't change. So this phenomenon is called diffraction. So the other thing, we call refraction and reflection if these waves bend like this, but here velocity doesn't change. In refraction, velocity must change when this wave enter from one medium to another medium. So here velocity doesn't change. Without change of velocity, the wave bends, spreads at a sharp edge like this, or bending as they say in the problem. So that is why there is another word for this phenomenon. Velocity doesn't change. If velocity doesn't change and the wave bends at a sharp edge, that is called diffraction. If velocity change, under change of velocity, due to change of velocity, if waves bend, that we called refraction. So if we use the two sharp edges, we can see the diffraction pattern is like this. At both sides, the wavefront bends. So this is called diffraction, is spreading like this. So that is diffraction. So therefore the answer is diffraction for this question. So as usual, we discussed the other answers also. Therefore I will explain little bit the other answers also. So before we go to the other explanation of this 1, 2, 3 and 5, I have to say something in this something special in this topic, diffraction. So if you have a problem, why, if you don't understand why these wavefronts bend like this, if there is no velocity difference, because we are used to this one, refraction, we have no problem there. In refraction we can understand, but here there is a problem without medium, without difference in medium. Why these wavefronts bend like this? So that is explained by this principle, that is called Hens principle. So since it is not in our syllabus, I am not going to explain it much, but I can say a little bit. The Hens said that this all the points in a wave front, so we can draw infinite number of points like this. So let us consider a few like this. So all these points act like a wave source. We know if it is a point source, the wave fronts are circular like this, circular like this. That means if we using the ripple tank, we can explain it. If we use the stick and touch it this water surface and move here and up and down, what happens? This water surface begins to make wave fronts, because we vibrate at a slow rate. So there will be waves like this, circular wave fronts will be generated like this. So the same way, since this is a point source, there we can draw a that point generates wavefronts, circular wavefronts like this. So that wavefront is the source to create this second plane wavefront. So how it happens? We have to draw lot of wavefronts like this, because there are infinite number of points along this plane wavefront that we have drawn in red color. So if we draw a number of wavefronts like this closer, what happens? This edges are overlapping from each circle and make this second wavefront. This one is the second wavefront. So here, why this bend, why this wavefront is bending, we can explain. If we draw according to that principle, the wavefront here, like this is the place, the origin of this wave, this place, the center. So this circular wavefront is alone there, no other wavefronts here to make that overlapping point, overlapping place to convert into a straight line. There's no one is helping, no other wavefronts, circular wavefronts, no other wavefronts, because this sharp edge is there. Only the end of this wavefronts is this place. So there are wavefronts here, to this side there are wavefronts, but to this side there are no circular wavefronts. So therefore this limit has only one wavefront, therefore this circular shape appears. Therefore nobody is there to straight make this wavefront straight. If the other wavefronts are there, if the other wavefronts are present here, so all overlapping on one another, this curve shape disappears and the straight line appears here, like this. So I draw it magnified like this, a straight line appears. But if the number of these circular wavefronts are infinite, these ripples we can't see, it is exactly a straight line. So like that he has explained how from a wavefront the other wavefront is generated. So using that principle we can explain that, like that, why this bend is there. So that is not in your syllabus, so therefore I don't think of it much. So let us go to now these are the answers. So now children, let us discuss in brief what is reflection is. So we need a good reflector for that material. Good reflector, that means a mirror which is made of silver. Actually we need a sheet of silver. So a plane or curved, doesn't matter. So if a ray, incident ray, falls on this boundary, what happens? It changes its direction to the same medium, like this. So that phenomenon is called reflection. That is called reflection. So we have to draw a normal line perpendicular to the boundary at the incident point. So then the rule is this angle equals to this angle, incident angle is equal to reflected angle. So this one is, if say this R, so I equals R. The next rule is the incident and reflected rays and the normal at the point of incidence. At the point of incidence, all lie in the same plane. So this one is right angle to this boundary. So all these three, this one and this one and this one, lie in the same plane. That means we can draw on a paper. It doesn't jump, this reflected ray doesn't jump out of the plane like this. Therefore we can draw it on a normal paper, plain paper. So that is the idea. So since we are talking in this advanced level class, we can go further in this topic, reflection. So frequency, if we consider this as a wave, there is a frequency. The frequency of this incident ray is equal to the frequency of this reflected ray, and the lambda, the wavelengths, are also equal in each case. Also there is another variable, velocity. Velocity also equal because both rays are in the same medium. And what is the other variable? If it is a wave, there must be a amplitude. This one, amplitude. So amplitude, say here amplitude is like this. So it is smaller here. Amplitude decrease. Amplitude decreases. Say A1 here, A2 here. So A2 is smaller than or less than A1, because at this point when this incident ray falls, some energy is lost. Therefore this amplitude decreases like this, decreases. So it decreases like this. So that is the thing we can discuss particularly in this. So now let us discuss in brief what is refraction is. So here we need a medium, transparent medium such as water or glass, not like silver. So here if there is an incident ray like this falling on the boundary of this between these two mediums, we call this one medium 1 because the incident ray is here. We call this one medium 2. So velocities must difference here. Say velocity v1 here, velocity v2 here. If this is glass, we know velocity is less than, v2 is less than, so let's write other side, v2 is less than, velocity of light is less than, v2 is less than v1, because this medium is air, easily it is fast, in this one slow, light travel slowly. So therefore velocity is v2 is less than v1. So due to that change in velocity, what happens here, we have to draw a normal to the boundary at the incident point. So if the condition is like this, the refracted ray it was heading this way, so it turns a little towards the normal, making this angle smaller. This one we say R, this one we say I. So the relationship is, if the refractive index is n equals, we know, sin I divided by sin R. So it is equal to refractive index, not defined as refractive index. refractive index is defined in terms of velocities. In terms of velocities, how it is defined as the greater one V1 divided by V2. So for glass we get 1.5, you know, that everybody knows. So this is refraction. So here if we consider this as a wave, we can discuss a little bit more. The frequencies are same. Why? They ask why. They have asked in past papers. The answer is the same source. There must be a source, vibrator here, or a light. If it is a light wave, a torch or light source, there must be some source. So the source is same for these two rays. Therefore, the frequency must be same. The velocities, now we know V1 is greater than V2. Then refractive indices, this one is smaller according to this condition. N1 is smaller. Actually, if it is air, the value is 1, we know. From air to glass, this one is 1, this one is 1.5. So that is the relationship between refractive indices. Then lambda. Lambda we have to substitute to the equation V equals f lambda. Say here the lambda between these wave fronts, say lambda 1, then the wave fronts here lambda 2 are smaller because the frequency is same. So frequency is same. If V decreases, the lambda must decrease because V2 is a small value according to this case. According to this case, it is smaller. So therefore lambda must be smaller, lambda 2 must be smaller. So we can write lambda 1 is greater, lambda 2 is smaller. So because the frequency is same, and we have to use these values how we assumed, like this. So according to that we have to determine whether it is lambda greater or smaller. So this is and also we have to discuss still the amplitude. Amplitude, if we say A1 here and A2 here, always there is a partial reflection. A small amount of the ray reflects from this point of incidence. So here, so therefore amplitude A2 is smaller than A1 a little bit, not little bit, according to this angle. According to this angle, if this angle is greater, this one is more smaller because this portion increases then. So that is refraction. So then before we go to a conclusion, we can write N1, the Snell's law, N1 sin I equals N2 sin R. That is called Snell's equation. That also we use. How the refractive index and the angle, this one, at same side we have to take N1 sin I. So this one I, so N here the same side. So N2 sin R, the same side we have to take. Don't keep in your mind 1 and 2. So if you keep in your mind like that, you won't make any mistakes. So let us that is enough for this refraction. So let us go to this third one. So now let us discuss what is interference is in brief. So there are two types. One is reinforcement, other is cancellation. So other is cancellation. So let us look what are they. So there is a wave like this. So this one is the crest, this one is the top. So imagine that this is a wave propagating on a water surface. There is a mechanical wave. So water is like this under the surface. Surface is oscillating like this. The boundary is the surface. So then this one is going to be a water particle. Water particle. So imagine another wave from somewhere, say this from this direction, propagate and come and overlap on this point like this, so that crest to crest overlap. So the crest of this blue wave and the crest of this black ray, they are overlapped on each other. So what happens, this black color wave has positive amplitude. That means like this, positive portion. So the blue color wave also has this positive portion, because the center line is here, axis of the wave lies like this. So the positive portion is overlapped with the positive portion of the other wave. So positive. Then the resultant is 2 times, if this one is capital A, the amplitude is capital A. So 2 times a wave is generated, having amplitude 2 times a, roughly 2 times a. So that type of interference is called reinforcement. So reinforcement can happen like this also. If the wave is like this, the black color one, and the green color one overlaps top to top like this. So this one is the water particle. This one is the water particle. Then the negative amplitude like this. Negative amplitude of both waves overlap each other. So if we plot it on a graph, the negative part like this of the blue wave, and the positive part, negative part of the black color wave, both to the same direction. So then we get a negative wave like this, 2 times height. If I explain it in another way, like this. So imagine this upward direction is positive. So the water particle is like this. So in this example, positive overlap each other. That means by the wave, this water particle is pushed to the positive direction, and also by the blue color wave also it pushes to the positive direction. So Therefore, the resultant is higher. The resultant is higher. A big force is acting. Therefore, so we get a reinforcement like this. The result happens. So then you might imagine that only one side, only to one direction that the force is applied, then oscillation must be like this. So how can it oscillate? Imagine a simple pendulum. So to oscillate, we don't have to push it from both sides. If we pushed it from one side is enough. The oscillation continues. So like that, the oscillation continues with an amplitude 2 times. So that is reinforcement. Negative or positive, doesn't matter. Positive, positive or negative, negative. So this side negative, I have marked it as positive. This must be negative. This one positive. So now let us discuss what is cancellation. To happen cancellation, the opposite portions of this wave, this positive portion is here now. So imagine this water particle is here like that. So the other wave overlap with this wave like this, the trough with this crest. So what happens? Cancel each other. Positive to negative. Positive to negative cancel. So therefore we call it cancellation. Positive black color positive, then green color negative, like this. So the resultant is 0. Therefore we say cancellation for that incidence. Cancellation interference is like that. So if I explain it using this particle, water particle, by that black color wave, since it is to positive like this, it pushes this water particle like that to the positive direction, and the blue color wave pushes this one to the negative direction. So no oscillation occurs, therefore. So that is called therefore cancellation. So next thing is, due to this interference, we can see interference patterns on a water surface. So if the water surface is like this, and the vibrators are like this, one vibrator here, the other here, 2 vibrators we need. Vibrators means we can vibrate, these are sources. So this vibrator oscillates on this touching this water surface. We have to adjust it so that it touches this water surface and also this one. So when we start this vibrators, those two, both of them should have same frequencies and same pace. Pace means when this one goes positive, this one also should go positive, synchronize. That is what we call pace. So after starting the vibrators, we can see circular shape wave fronts like this. Circular shape wave fronts like this. They propagate to each directions. So this one also starts to distribute wave fronts, circular shape wave fronts like this, and at some places we can see that reinforcement occurs. at some places we can see cancellation occurs. So due to that we can see a pattern. Pattern means blanks like this, no waves. There are no waves at some lines like this. So there is a pattern, we call that interference pattern. So if these waves are radio waves, then at these places the radio doesn't work. No waves, no signals. Therefore it doesn't work. So at these points where reinforcement occurs, the radio works well. Radio works well, so the signal level is high. So that is the interference. So here these two sources must have the same frequency and same pace. So the single word is monochromatic. Monochromatic sources. We say monochromatic sources. So that is interference. Let us now take this one, total internal reflection. So imagine a glass cube like this. We can discuss it using ripple tank even, but this one is easier. So if the velocity of light, say here v1 air, here v2, and here again v1, again v1 air. So if this velocity v2 is lower, like in glass, if this if this ray tries to penetrate from this, coming from this medium whose velocity is v2, smaller, velocity is smaller, and trying to leave to a medium whose velocity is higher, as in gas. Say this one is 1.5 index. If the velocity is smaller, the index is higher, 1.5. Smaller means the wave is slow here. Wave is slow here. Here fast. So 1.5, here the refractive index is 1. Then what happens, this emergent ray, it was previously heading this way, but due to this velocity change, it bends like this away from the normal. That you know, away from the normal, because from a denser medium to a rare medium, when this ray travels, this happens. So if we increase this angle, say like this, if we increase this angle, it was earlier smaller like this, now we increase this angle. So what happens, the emergent ray, it was leaving like this earlier, now it bends further towards the this boundary. Then at one time, as we continuously increase this incident ray and incident angle, there is a time it goes along this boundary. So then that angle is called, the incident angle is called C, that is total the critical angle, we call it is critical angle. So if we increased furthermore a little bit even, what happens, it reflects to the same medium like this, according to the rules of reflection, reflect. So this angle cycle like this. So this phenomenon is called total internal reflection. So velocity equals frequency equals, then wavelength lambda equals, and also amplitude equals, because no light is leaving like this, penetrating totally, the light reflects. That is why we call total internal reflection. So this phenomenon is used to bend, to reflect lights where it is necessary, without using mirrors, because if we used mirrors, this final amplitude is less than the initial one. Therefore the intensity of the image goes low. Therefore in instruments like these microscopes, so we have to bend like light like this. If it is a stereo microscope, we have to divide it into two, split it, and to both eyes we have to direct. So therefore we have to use mirrors. But if we used mirrors, the amplitude decreases from one to another, then therefore final image is very dark. Therefore they use, who make these things, these cubes and prisms, and total internal reflection is used there. So this is the final one. And also I have to mention you that the equation we know, n equals 1 divided by sin c. So that equation we use to calculate if we happen to. So that is it.